In this section, we're going to look at complex numbers. Complex numbers are a group of numbers that are actually encompassing the real numbers. The definition of I is going to equal the square root of -1, and the standard form of any complex number is going to be a plus bi. Now, when we have that standard form, a and b are always going to be members of the real numbers. B is always going to be the coefficient of the I. This helps when we have negatives underneath the radical. Before, if we had the square root of -25, we would just say it's not a real number because we know we're not allowed to have a negative under a square root. Since we now know the definition of I, we can break that down to the square root of -1 times the square root of 25. Well, we know that the square root of -1 is our new definition for I, and the square root of 25, of course, would be 5. So the square root of -25 can now be called 5i. In standard form, that would really be 0 plus 5i, where a is 0. b, or the coefficient of I, would be 5. We can look at something like the square root of -18. If we were going to try to clean that up, the first thing we're going to do is break that square root of -1 away. Then we'd have times the square root of 18. Well, 18, if we break it down into its prime factors, is 9, or 3 times 3, times 2. Cleaning up our square root, we have 2 3's under a square root, so we get to pull 1 3 out, leave the radical of 2, and make that square root of -1i. And you will usually see these written as 3i times the square root of 2. We don't usually put the I under or at the end of the radical, although it would not be wrong, but it's very easy to extend your radical too far if you write sloppy, and you don't want anyone to think that your I is actually underneath that radical. We can look at powers of I. If we look at I to the second power, that means I times itself twice. With our definition, that's the square root of -1 times the square root of -1, which means we have 2 of these -1's underneath the square root, therefore we get to pull 1 out. So I squared is actually equal to -1. If we looked at I to the third power, that's really I times I times I, or the square root of -1 times the square root of -1 times the square root of -1, meaning that we have 3 of the -1's under a square root sign. It takes 2 to pull 1 out. So if we pull a -1 out, we're left with 1 of the -1's underneath the radical, and changing that back to its definition is just going to be -I. I to the fourth power is equal to I times I times I times I. That means underneath that radical we would have 4 of those -1's. It takes 2 underneath the square root with the index of 2 to match before we can pull 1 out. So this time we actually get to pull 2 of the -1's out from underneath the radical, and there's none left in. Well, -1 times -1 is going to be a +1. It's going to be very helpful if you will remember that I squared is equal to -1. I to the third is going to equal -I, and I to the fourth is actually a real number, a +1. When we have i's to powers that are higher than 4, you can break those down according to your fourth power. For example, if you have I to the 9th power, we can rewrite that as I to the 8th power times I, because we know that I to the 4th power is actually 1. 1 squared would just give us 1. So I to the 9th power would just be the same thing as a regular I. Just think of your multiples of 4 if you're trying to break down the I to the higher powers. Let's look at one more. Let's look at I to the 29th power. Well, the closest multiple of 4 to 29 would be 7. So if we write I to the 4th raised to the 7th power, that's going to give us 28 of those i's. We'll need one more I. that's really going to be 1 to the 7th power times I, or just a plain old I. When we add and subtract complex numbers, we need to recall that a plus bi is going to be the standard form. So if we're adding two of these together, you are going to combine the real parts, or the a's, and then you'll combine the complex parts, or the b's. Let's look at the complex number 2 plus 3i, where the a is 2 and the b is 3, and add together 5 minus 3i, where the a is 5 and the b is negative 3. To add these together, it's combining like terms. We take the 2 and the 5 to get 7. We take the positive 3i and the negative 3i, which will actually cancel out. So the answer is 7. Now in a plus bi form, that would be 7 plus 0i, where the a would come out to be 7 and the b would be 0i. But we can clean that up just by saying that that's 7. Let's look at another one for subtraction. Let's look at 8 plus 4i plus 9 minus 2i. Combine the real parts, the 8 and the 9. That's going to give us 17. Combine the imaginary parts of 4i and a negative 2i, which will leave us with a positive 2i. Subtraction is going to be the same thing, except for we do need to remember to distribute the negative. If we have the same example, 2 plus 3i minus 5 minus 3i, before we begin, remember to distribute that negative sign. So we really have 2 plus 3i minus 5 plus 3i, because a negative times 5 is negative 5, and a negative times a negative will be a positive. Combining the real parts, 2 and negative 5, will give us the total of negative 3. Combining the imaginary parts, 3i plus 3i, will give us 6i. So in our answer, the a is negative 3, the b is positive 6. Let's look at one more example before we leave adding and subtracting. If we take the 8 plus 4i and subtract a 9 minus 2i, we want to again remember to always distribute that negative. We'll really have 8 plus 4i minus 9 plus 2i. Combine the real parts of 8 and negative 9, which will leave us a negative 1. Combine the imaginary parts of 4i and a positive 2i, which will leave us a positive 6i. If we want to multiply together complex numbers, our powers are really going to come in handy. If we multiply together 3 plus 2i times 5 minus 7i, this should look familiar. It's two binomials multiplied together, which you either think of as the distributive property or the FOIL. First times 3 times 5 will give me 15. Outer terms 3 times negative 7i will give me negative 21i. Outer or inner terms 2 times positive 5 will give me 10i. And last terms 2i times negative 7i will give me negative 14i squared. Now if we clean up our like terms, that's going to give me 15 minus the 11i's minus 14i squared. But notice that is not standard form of a complex number. We want to leave complex numbers in a plus bi form. So we need to get rid of the I squared. Keep in mind that I squared is the same as negative 1. So if I replace the I squared with a negative 1, negative 14 times negative 1 is going to be a positive 14. At that point, I can combine it with the real number of 15. 15 and 14 will give us 29 minus the 11i. So we now have that in a plus bi form. Let's look at one more before we go on. Let's look at negative 2 minus 8i times 5 minus 6i. Again, distributive property. Negative 2 times 5 will give me a negative 10. Negative 2 times negative 6i will give me a positive 12i. Negative 8i times 5 will give me a negative 40i. and negative 8i times negative 6i will give me a positive 48i squared. At this point, we'll bring the negative 10 down. We'll combine the 12 with the negative 40 to get a negative 28i. And I'm going to go ahead and replace the I squared with the fact that that's negative 1. That's really going to be minus 48. So if I combine the negative 48 and the negative 10, we'll end up with negative 58 minus 28i. You can divide with complex numbers also. In dividing with complex numbers, it's helpful to recall your intermediate algebra or your high school algebra 2 for conjugates. If a plus bi is our standard number, a minus bi is going to be its conjugate. Remember, conjugates keep the same a and b, except for we change the plus to a minus sign, or vice versa. Because if we're looking at dividing a complex number, if we have 2 plus 7i divided by 3 minus 2i, i's are kind of like radicals. You don't want to leave them in the denominator of a fraction. So in order to rationalize this, is what you did with the actual radicals, we want to multiply both top and bottom by the conjugate of the denominator, which would be 3 plus 2i. We do this because we remember that anytime we multiply a number times its conjugate, the outer and the inner terms are going to end up canceling out. If we did the full distributive property on there, we would have the plus ab in the middle, minus ab. Well, a positive ab and a negative ab will cancel each other out. So a minus b times a plus b is always going to give us a squared minus b squared. If we look at the denominator, 3 times 3 will give us 9. We know the outer terms of 6i and the inner terms of negative 6i will cancel out. And the last terms, a negative 2i times a positive 2i, is going to be a negative 4i squared. On the top, we're going to FOIL out. 2 times 3 is going to be 6. 2 times 2i will be 4i. 7i times 3 is going to be a positive 21i. And 7i times 2i is going to give me a positive 14i squared. Now we want to clean up. We want to combine the middle terms. Well, the middle terms on the top will combine for a positive 25i. We're going to replace the I squared with the value of negative 1. So plus 14 times a negative 1, which would be the same thing as minus 14. We'll do the same on the bottom with the I squared. Instead of 9 minus 4i squared, we're going to have 9 minus 4 times negative 1. The top, or the numerator, will be 6 plus 25i minus 14. The denominator will be 9 plus 4. One last step in cleaning that up, combining the real parts. On the top, a 6 and a negative 14 will make a negative 8, plus that 25i. On the bottom, 9 plus 4 will be 13. Now, you can leave it sandwiched up for this, but if you were talking about the a plus bi form, your a would be negative 8 over 13, and your b would be 25 over 13. Because we remember, this is the same as that 13 going to both of those terms. You don't have to actually write it out like this, as long as you realize that the a is negative 8/13 and the b is positive 25i over 13. Let's work one more of these before we leave complex numbers. Let's take 6 plus 7i divided by 3 minus 8i. Again, we don't like the i's in the denominator. We want to rationalize this by multiplying top and bottom by the complex conjugate of the denominator. That wants to be 3 plus 8i. That way we know when we multiply on the denominator that the outer terms and the inner terms will cancel out. So our first terms will be 9. Our last terms will be minus 64i squared. Now if you want to keep working that denominator, That's going to be 9 minus 64 times negative 1. That's going to be 9 plus 64, or that's going to be a 73. On our numerator, using our distributive property, 6 times 3 is 18. 6 times 8i is a positive 48i. 7i times 3 is a positive 21i. And 7i times 8i is going to be a positive 56i squared. That's going to be 18. We're going to end up with 69 of the I terms when we combine like terms. And we're going to change the I squared to a negative 1. So we'll have plus 56 times negative 1. That's going to be the same thing as 18 plus 69i minus 56. Combine your like terms of a negative 56 and a positive 18. You're going to get a negative 38 plus 69i, all divided by 73. It's the same thing as saying negative 38 divided by 73 plus 69i divided by 73.